Hello, everyone. This is my first face-to-face ORAN meeting, and I'm excited to be here. It's great to see so many familiar faces whom I have previously known only virtually. My name is Volkanos Çelik. At Broadcom, my key areas of focus are securing the xApps, rApps, and our overall ORAN SMO offering. In addition, I am one of the 5 chairs of the SPIFFE Steering Committee, or SSC. The SSC is the sole overseer of the full spectrum of SPIFFE-related work, and it acts as the final decision-making body for everything related to SPIFFE. I also lead the architecture of VMware Secrets Manager, which is a zero trust cloud native secrets management solution that leverages SPIFFE as its identity control plane. And being at the intersection of ORAN, SPIFFE, and zero trust security has given me a unique perspective on the challenges and innovations in securing an open and scalable network. And I'm eager to share some of these findings with you today. Here's how our agenda will roughly look like. We'll start by exploring fundamentals of SPIFFE and SPIRE. Next, I'll briefly discuss some of the use cases of SPIFFE and SPIRE in real-world scenarios. Then we'll explore how SPIFFE can be utilized to manage ORAN identities effectively. And finally, we'll transition into a fireside chat with Daniel Feldman, a subject matter expert in SPIFFE, SPIRE, and also a well-known name in the Zero Trust security community. So without further ado, let's dive in. I'll start with SPIFFE and SPIRE. So what's SPIFFE? SPIFFE, or the Secure Production Identity Framework for Everyone, aims to establish a universal identity control plane by setting a framework of standards. The SPIFFE identity model assigns each service a unique identifier known as the SPIFFE ID, and SPIRE, the SPIFFE runtime environment, is a reference implementation of SPIFFE, and SPIRE is a CNCF graduate project. The graduate title means that it is mature and it is stable to be used in production at a massive scale. And Spire has been battle tested in large scale environments actually, and it is secure and ready for production, as I said. So this is the official definition of SPIFFE from the official SPIFFE.io website. SPIFFE and Spire provide strongly attested cryptographic identities to workloads across a wide variety of platforms. Well, it's a bit mouthful, so let's disaggregate this definition to make some sense of it. I highlighted certain keywords out here. Some of these terms you might know, some you might not be familiar with. Some might have different connotations in the context of SPIFFE, so I'll cover them all regardless to establish a baseline of understanding. So attestation refers to verifying an application's identity and integrity off cycle without talking directly to the application. So SPIFFE ensures that the app is what it claims to be by using what's called external verifiable evidence. So without directly communicating with the application itself, SPIFFE talks to the platform that hosts the app, for example, or the cloud provider or the orchestrator to get some meta information about that app. And with that meta information, it correlates and identifies the application, as we'll see examples of it soon. There are 2 forms of attestation in the SPIFFE lingo. One of them is node attestation and the other is workload attestation. We'll see examples of these shortly as well. And when I say workload, it's just a fancy way of saying an app or a service. In this talk, I'll use the terms app and workload interchangeably. And in the context of ORAN, things like xApps, rApps, or CM configuration manager, for example, are all examples of workloads. Apps are identified by their cryptographic identities. In SPIFFE, these identities are called SVIDs, or SPIFFE Verifiable Identity Documents. And SVID is just a fancy way of saying X509 Digital Certificate. SPIFFE ID is a human-readable identity that the apps use. It is embedded in the SAN, Subject Alternative Name field of the X509 SVID. And related to identities, there is the concept of a trust bundle. A trust bundle includes the public search that is required to validate the cryptographic signature of the SVID and also other applications' SVIDs that the application wants to talk to. SPIFFE is a platform agnostic protocol. It can operate across various computing environments, across cloud environments and cloud boundaries, infrastructures without being tied to any specific technology or any specific vendor, which makes it an excellent fit for O-RAN. And finally, the SPIFFE Workload API provides an interface for the apps to obtain the SPIFFE SPIFFE IDs trust bundles. It abstracts the complexities of certificate issuance, renewal, and revocation. But having learned these basics, why we need SPIFFE? Let's discuss why there might be a reason to use SPIFFE. So these are some of the headlines I gathered over the last few weeks, and many of such incidents happen almost weekly every time. Why? Because without an identity framework, applications end up bundling things like secrets, service keys, service tokens together with the apps itself. And when any secret is a part of the application's deployment, then it's a vulnerability waiting to be exposed, as we see the examples here. So we need a method to distribute those identities as certificates to the applications automatically and at scale. Because like for an O-RAN deployment, I may have like thousands of xApps distributed across a wide nationwide network. I cannot manually rotate all the certs. I need an automated way, and I need to do this fast. And we need to do that without inherently trusting the applications as well, because that's the whole point of zero trust architecture after all. Moreover, to ensure sufficient security, these identities or certs need to be, like I said, assigned and revoked automatically. They need to be cryptographically and irrefutably verifiable to ensure that the identities can be trusted without any question. They need to be short-lived. A traditional certificate has a TTL of like a couple of months to a year to even sometimes tens of years, depending on the kind of the cert. But in SPIFFE, the typical lifetime of a certificate is a couple of hours. And by short-lived, I mean that a certificate should not exceed a couple of hours to minimize the window of opportunity of misuse in the case of a certificate leakage. So also, we need a standardized and portable means to identify applications through certs across platforms, machines, and cloud boundaries to maintain security and consistency and interoperability. So let's see how SPIFFE aligns with these needs and wants. Firstly, as we mentioned, SPIFFE automates this entire process of certificate issuance, renewal, and revocation. And also, unlike traditional security measures that may have a lifespan of months or even years for certificates, SPIFFE issues certs with TTLs that last only a few hours. This is configurable, but a couple of hours to a day is a ballpark default that is used among various applications that I have seen so far. And this drastically reduces the potential damage in a security breach, as compromised credentials lose validity real fast, real quick. In addition, SPIFFE almost entirely, I cannot say completely, but it almost entirely eliminates the need for using a secrets manager, because with SPIFFE, you don't need keys, passwords, service tokens to identify apps, because the SPIFFE ID is the app's identity itself. It can identify itself cryptographically without any doubt to any other application by providing its SWIT. Moreover, with SPIFFE, there is no need to maintain CRLs, certificate revocation lists, because SPIFFE's approach of short-lived certificates obviates the need for CRLs, as the certificates are very short-lived, they expire really fast, and by the time you need a CRL, the certificate will not be valid after all. In addition to all this, SPIFFE is agnostic, it is platform agnostic, and it is mesh agnostic. So this flexibility ensures that no matter where your services run or how they are managed, SPIFFE can provide a consistent and reliable identity management system. Also, SPIFFE's architecture is plugin based and extendable. So, for example, if you find a plugin that uses SPIFFE in a certain way, like interacting with a database, for example, but it doesn't quite suit your needs, you need to slightly tweak it to bend it to your will, Well, you can do. It's plugin based. You can fork that plugin. You can write your own plugin. And because of this plugin based architecture, SPIFFE becomes essentially whatever you want it to be. And lastly, SPIFFE is a recommendation in NIST's Zero Trust Architecture Guideline in document 802.7. And adopting Zero Trust Architecture is essential. That's why we are working really hard here to publish a paper about ZTA this June 2014. So, who uses SPIFFE? Well, essentially, it's everyone. Due to time constraints, I won't list every company displayed here. However, to give you an idea of the scale at SPIFFE is deployed, let's consider one standout example, ByteDance, better known as TikTok. ByteDance operates the largest known SPIFFE deployment in the world. A couple of years ago, it can be maybe 4 years, it was operating like more than 1 million nodes of SPIFFE across the globe. So it really operates at a massive scale, effectively and securely, which proves that SPIFFE can indeed scale. And here are some other tools and services that that uses SPIFFE. Again, in the interest of time, I'm not going to list them all, but I want to highlight two significant examples. One of them is Google Cloud, GCP, which uses SPIFFE for workload identity and authentication, ensuring that secure service interactions across its vast cloud infrastructure is established. And the second is Microsoft Azure Active Directory, which again leverages SPIFFE for workload identification and also federation, enhancing security in its own distributed, massively scaled environments. I am going to quickly overview some of the SPIFFE use cases to give an idea of what SPIFFE is capable of. This one is about platform and infrastructure independence. SPIFFE uniquely is capable of dispatching unified identities across different environments. This means using SPIFFE, an application in Google Cloud can communicate to another application in Amazon Cloud and then talk to yet another application on your on-premises edge cluster, edge data center, for example. So we can establish a secure heterogeneous way of communicating applications through MTLS by just using SWITs minted by a federated SPIFFE architecture. Uh, and you can also use SPIFFE to secure your supply chain. You can use SPIFFE to ensure that only the containers that is created by your CI/CD pipeline receive a valid identity. This will really help you because in the case of some adversary injecting a rogue container in your system in however means, the container won't be able to get an SWIT because the SWITs will be only distributed to the containers that are created by your CI/CD pipeline, which secures your system and ensures and protects your supply chain drastically. And this is about simplified access to resources using SPIFFE. SPIFFE allows the use of various plugins, such as the OIDC Federation plugin, to facilitate secure communications with things like databases, object stores, message queues, and various other apps like Kafka, Minio, and the like, without the needs for using usernames, secrets, or credentials. So I can use the SPIFFE ID of the application transparently to authenticate to a database via MTLS without needing a credential, which is amazing. And this one is related. It's about doing this in the cloud scale. You can also authenticate to cloud services like Amazon RDS or Amazon S3 or some Google Cloud Store without needing any authentication or credentials by just using your SWIT or SPIFFE ID. And this is about enhancing security through compartmentalizing your trust boundaries. To minimize the attack surface, you can divide your security boundaries into several trust domains. And with SPIFFE, these domains can be federated, allowing for secure communications based on well-defined and secure relationships. For example, this near real-time rig and non-real-time rig can operate with their respective trust domains, and with federation, they can securely interact with each other. Now, let's explore how we can authenticate O-RAN applications using SPIFFE. But just a quick note that These methods that I discuss here are potential strategies rather than established standards right now. So we are at the cutting edge in that regard. So please consider that what I present here today as a set of prescriptive suggestions. These are not definitive rules, but possible approaches to be refined and adapted by our standard CI, spec review, and commenting and discussion processes to push and evolve into standards. So with that caveat put aside, let's begin by discussing a scenario involving an xApp that wants to communicate with another application in the near real-time rig. So please remember that while I am using xApp as a specific example, these principles and methodologies we'll explore here today can also apply to any application or service operating within the O-RAN cloud. For these apps to communicate securely, we want MTLS, of course. And how do we establish MTLS? We want certificates. And to more specifically, we want X509 version 3 digital certificates to establish a secure MTLS connection. And luckily, SWITs are nothing but X509 version 3 digital certs. So this means we can use SPIFFE to dispatch certificates to these apps seamlessly and establish MTLS connectivity as a side benefit. Or more appropriately, we'll use Spire, since SPIFFE is the standard, if you remember, and Spire is a reference implementation of the SPIFFE standard. So let's go a little deeper and see how we can use Spire in rigs. But before I dig in a little further, I want to focus more on the Spire high-level architecture. And I'll talk about near real-time rig in these examples, but the implementation, like I said, will be similar in a non-real-time rig scenario or even for SMO and O-Cloud as well. So the Spire architecture consists of a centralized server and one agent in each virtual or physical machine. And the server, I show this as a single identity, but in a highly available setup, there might be more than one server that is like acting in a load balanced fashion, but it will act as a single identity. So for all practical purposes, we can think that there is a single server here. Apps fetch their certificates from agents using the SPIFFE workload API after establishing a trust, which we'll discuss shortly. And agents fetch the certificates the apps need from the server, again, after establishing a trust relationship with the server using the Node Attestation API that we'll see an example soon as well. And in the context of rigs, we'll likely be using Kubernetes as our orchestrator, and our architecture diagram will be more Kubernetes. So these are more or less the same, but we have some more control and structure over the entities. So Spire server in this case will be a pod in a stateful set. Spire agents will be pods in daemon sets, and workloads, which are xApps in our case, will be containers in pods. So each node will have one Spire agent that talks to the central Spire server, and the entire cluster will be a single trust domain for practicality and also for the sake of simplicity. And administrators can use the CLI, as you see the two little boxes at the very top of the diagram. And the software orchestrators, such as a Kubernetes operator, can use the gRPC registration API to create registration entries on the Spire server for the applications. In addition, the Spire server can optionally be configured to trust a provider's certificate authority. So this is optional, like I said. By default, Spire server mints self-signed certificates. But if we let the Spire server act as a intermediate CA, this will further harden the trust relationship, enhancing the system's overall security posture. And sometimes, for compliance reasons, we might need to do this as well, which is possible with SPIFFE and Spire. And in this example, we can delve a little bit deeper into the mechanics of it. And I hate using the word delve, but that's a different reason. If we examine the mechanics of this process more closely, the Spire server utilizes the upstream authority plugin to submit a CSR certificate signing request to the certificate provider's certificate service provider's certificate authority. And once it receives the signed certificate, it stores the cert in a trust bundle store. And the Spire server then uses the cert as it sees fits to communicate with the Spire agents, for example. So let's explore what happens next, the node attestation. So what we did so far is we established a trust relationship between the Spire server and the certificate authority, the two like spill buttons that you see in this diagram, the first and the second. And next we'll establish a trust relationship between the Spire agent and the Spire server. And after that, we'll establish a trust relationship between the Spire agent and the application to finish and finalize the circle of life, chain of trust, whatever you call it. And this next step is the establishment of trust relationship between the Spire server and the Spire agent. Here we are going to use the X509 POP point of presence attestation flow, but there are other flows, and an administrator can choose a different workflow to attest to establish the trust based on the infrastructure that they have, or the cluster's requirements, or other things as well. But in this flow, regardless, first the Spire agent initiates a TLS connection to fetch a Bootstrap trust bundle from the Spire server, and this bundle is essential for establishing a trust baseline. And in the blue box at the middle of the sequence diagram, in the zero knowledge proof challenge phase, the Spire server sends a challenge to the agent, and the challenge involves the agent signing a randomly generated text to confirm the validity of its certificate, to show that it indeed owns the private key that is linked to the cert. So in this scenario, both the servers and agents certificates are provided likely via off-cycle methods, like using an orchestrator or a CI/CD pipeline, for example. But there are other node attestation methods that include using trusted platform modules, such as the TPM version 2 ones that have been discussed by our friends at NIST this Monday at the Lunch and Learn. Or we can use cloud APIs, orchestrator APIs such as Kubernetes, or like cloud identities like AWS or Google Cloud Instance IDs. Since this is plugin based, sky is the limit to establish this trust relationship. And in our case, xApps will utilize this SWITs and trust bundles that are created after establishing this trust relationship to establish MTLS connectivity with other services. And once this trust relationship is established, in the repeat box down below, the yellow bordered part, the agent will periodically send certificate signing requests to the server. The server then signs the CSR the agent gives to it, and then the agents will be able to assign SWITs back at the and give the updated trust bundles to the applications that request it after establishing a trust relationship between the application and itself. So far we established trust between certificate authority and the server and the agent. And the next step is the workload attestation to establish a trust relationship between the agent and the application. And since we are using a Kubernetes cluster, this example will be more case specific. The Spire agents will in this scenario query the kubelet to confirm that the xApp meets certain criteria, and this criteria might attest that the xApp is within a designated pod, it carries certain labels, it is managed by a specific service account, or it resides in a particular namespace. And what this criteria will be is defined by the application's Spire server registration entry, as we'll see shortly. If there is no registration entry, then there won't be any attestation, and the application will not be able to get an SWIT. But once the application satisfies all these checks and balances, the Spire agent then takes on the responsibility to periodically send the application its SWIT and its necessary trust bundle. And the beauty of this process is this is automated, so we can do this as fast as we want, and that gives us the possibility to rotate the certs in hours rather than in months. And the time frame of this rotation is typically half the certificate's TTL. So if the certificate is going to expire in 4 hours, then this S-bit exchange will happen like every 2 hours. Additionally, the workload attestation is not limited to Kubernetes. The Spire agent is equipped with several plugins to handle diverse environment. For example, it can query the Unix kernel about the application's details, such as its process ID, user, group, or even the SHA hash of the binary or the path that the binary runs. And for Windows platform, it can again utilize the Windows API to perform similar attestation tasks. And it can leverage the systemd plugin to again verify the application's integrity off cycle. And these mechanisms ensure that regardless of the operating environment, operating system, or where this Spire agent is running, it can still effectively attest apps, reinforcing security across a heterogeneous cloud of applications in a system. So apps use SPIFFE IDs, but how does a SPIFFE ID look like? Well, it's something like this. It's just a string, but there are certain formats that it needs to adhere to be aligned with the standard. So it has to start with SPIFFE:// that's part of the standard. And then it needs to follow a trust domain, which provider.example.com here is the trust domain that this SPIFFE ID uses. But to be clear, this trust domain doesn't have to resolve to an actual DNS domain. It's just a string to identify a trust boundary. And the rest of the ID is mostly freeform. You can choose it however you decide to choose, but having a structure to it will help you to diagnose and monitor and audit things easier. In this particular example, NS near real-time rig indicates that the application is in a near real-time rig namespace. SA/TS xApp might mean that the application uses a traffic steering xApp service account, and VMTS xApp is likely a human-friendly alias for the VMware traffic steering xApp name. And the GUID that you see here, the ID/GUID, is highlighted in yellow, and it's the actual ID of the xApp, which is a UUID as defined by the O-RAN standards. And the beauty of this is we are adding and embedding an ID that is the standard ID of the application that is defined by the standards into a certificate, which means that this application can give the certificate to anything, anywhere. It doesn't even have to be an O-RAN entity, and whatever gets that ID can irrefutably verify, because this certificate is signed against a well-known and trusted certificate root of trust. So it can verify the authenticity, and then it can verify that this ID actually belongs to this application. To further bolster the security of our system, we can configure a cloud-based key management system to store things. But why do we need a KMS? Because all the time we send CSRs and sign certificates, and excuse me, whenever we send a certificate signing request, we need to sign something with a private key, and those private keys are rather kept private. And if we don't use a KMS, those private keys will be in the memory or in the file system of the Spire server and Spire agent, depending on how it is configured. But if we use a KMS, then the private keys will never leave the boundary of the key management system. So for example, when the Spire server wants to sign a certificate, it will just send the digest of the certificate to the KMS, and the KMS will sign the digest with the private key and send the signed thing back to the Spire server. This way, the private key will never leave the boundary of the KMS, and it will be securely protected in an entity that is designed to store sensitive stuff. And Spire server and Spire agent will not even be aware of the key itself. They will have aliases that point to the key, but they won't know what the key actually is, which will give an additional level of trust in the system. But regardless of how we establish this public key infrastructure or this dynamic key rotation scheme, the applications will eventually need to get the SWIT, because otherwise, how can the application identify itself? That's the whole point of SPIFFE. So applications, there are several ways that it can get an SWIT. The app can directly interact with the SPIFFE workload API. The workload API is just a Linux domain socket, so the application can plug itself into the socket and start listening to that socket and parse what's coming in. Or it can utilize one of the available SPIFFE SDKs to simplify the integration and management of this socket. There are SDKs available, as far as I know, in the languages including Go, Java, Rust, C++, and Python. And they abstract so much of a deal of complexity that, like, without using an SDK, it's like a burden. In VMware Secrets Manager, for example, we use Go SDK, and it's such a relief. Like, otherwise, it will be extra hard to establish that level of integration without any error. So if you want to programmatically talk to the workload API, I highly recommend using an SDK, but it's not the only way. And for certain applications, you might not even have a chance to use an SDK. For example, this might be a third-party xApp that we deploy into our cluster. We might not have the access to its source code, and therefore we might want to provide those certificates on the side to the app, which can be done by a tool called SPIFFE Helper. SPIFFE Helper is a convenient option that acts as a sidecar container, and that sidecar, as we see in this diagram, automatically mounts to the pod, and then it refreshes the certificates as needed without the application needing to handle the API interactions directly. And it's amazing from the point of the application, because the app doesn't know nor care about whether this existence of this entire Spire SPIFFE architecture. Whatever it sees is just a folder that has a certificate in it and also a trust bundle in it. And those trust bundles are valid, and it can always trust that the application can use it to establish MTLS, which is great. It's separation of concerns. It has its pros and cons. Personally, if I am developing my own applications, I prefer to use an SDK. If I am integrating with an application that I borrow elsewhere, I prefer to use a certificate sidecar. So that depends on your use case, essentially. And like the application to talk to anything in the cluster or to attest itself, it will require a Spire server registration entry. And there are several ways to register an application to the Spire server. And in the context of O-RAN, a particularly fitting approach involves utilizing the service management orchestration framework. The SMO can communicate with the Spire server through the standardized O1 interface to create application registration entries. And once the registration entries are saved in the Spire server, then the Spire agent can send the CSRs to the app for the app's SWIT, and then fetch the SWITs and the trust bundle for the apps as usual. And this repeat loop, like I said, it repeats in the context of hours, and that's how we can automate this certificate exchange real fast. And also the benefit of it is the application doesn't have to exist for this cycle to start. So the app will start as soon as it can. The Spire agent will get the SFITs as soon as possible, and when the application starts its life cycle, it will immediately fetch the certificate and start identifying itself and securely authenticating with the rest of the cloud without having to wait for the CSR to be signed, ideally. And an important aspect to consider is handling the app registration on the Spire server. And as a side note, like I said, the app doesn't need to be actively running to be registered to the Spire server. And this is a critical feature because it ensures flexibility in how the applications are deployed and how their life cycle is managed. So when a registration entry is created for an xApp, the Spire server caches those SVITs and holds onto them until an xApp can, or any app actually, can verify its authenticity. And once the app is attested to be authentic, the agent sends the SVITs and the trust bundle to the app. And there are two ways to do this. We can either do this programmatically through the Spire server's gRPC API, or we can use a custom resource called cluster SPIFFE ID, which is a more declarative, more cloud native way. And it is my preferred way of doing things that I'll discuss why soon. And it makes managing and scaling things easy at a cloud native, dynamic, highly scalable environment. But regardless of the method, whether we use direct API calls over declarative configuration, or whether we use the cluster SPIFFE ID abstraction, the end result remains consistent. The Spire server is equipped with the necessary registration entries to mint and distribute SVITs to the apps. So we talk about cluster SPIFFE ID. So how does it look like? It's something like this. It's a custom resource. And if you squint hard enough, you can see that it feels like a syntactic sugar around the registration API of Spire server, but it's a little bit more than that. For example, this SPIFFE ID template that you see in the middle helps configuring things in a clear, definable way. Since you have a template for the ID, everyone have a certain standardized way of defining IDs. The teams and applications won't go in their own way to define their own IDs. It will be easier to parse, interpolate, monitor, and audit these IDs in this case. In addition, the cluster SPIFFE ID contains the selectors, the similar selectors that you see here actually, and also workload selector templates. So we can say that for an SVIT to be assigned to the application, the application needs to match these labels given here as name vSecond Sentinel and part of vSecond system, and it has to have the vSecond Sentinel service account, and it has to be in vSecond system namespace. The cluster SPIFFE ID is a declarative way to define this. But the beauty of it is not this declarative definition, if you ask me. It is because the cluster SPIFFE ID is a Kubernetes resource, we can use regular K8s methods to describe it. So if we do a kubectl describe cluster SPIFFE ID, or if you do a kubectl get cluster SPIFFE ID, then you'll see like something similar to this. It is the same like labels and like selectors and things like that. But the more important thing is this, pod selected one, the green text down below. It shows that right now, in this instance, there is one application in the cluster that matches this criteria. One application in this cluster is inside the vSecond system namespace. It has a Keystone service account, and it is matching the labels that we added in this pod selector template. So it is eligible to get an identity and SVIT on its own. So this is like a heaven if you are an SRE, site reliability engineer, or if you are a security engineer. This data is really useful to audit and identify which app is getting what kind of an ID, which otherwise, if you are using the non-declarative method, if you are talking to the registration API directly, then you'll have to write some custom code in the first place. And secondly, you may need to design this observability layer yourself around this architecture, which I personally prefer not writing code whenever possible, because no code is more secure than some code. So this is my preferred approach, but it's not the only way. As I said, you can directly communicate with the API as well. And this is how the registration entries will look in the server. It's like a database entry, and indeed it is a database entry actually. So it has the SPIFFE ID, and it has these selectors and some other metadata as well. And based on this registration entry, the agent will attest the application. The agent will look into the registration entry and attest the application to have like the namespace, service account, and even the pod UID that we define here. So those are the entries, but there is this is kind of the like blueprint, but there's the actual certificates that the application uses to authenticate itself. Then, I'm a visual learner, so I want to visualize things, and I wanted to see those certs and how they look like, and this is how they look like essentially. So these yellow things are the trust bundles that the application will use to verify the integrity of its SWIT and also other applications' SWIT by checking the trust chain of the certificate from itself all the way to the root of trust. And this green thing is the SWIT that the application receives, and it is signed by this private key, the blue key that you see down here. And like we said, the private key can also be in a KMS. It doesn't have to be in the memory of the server. Keeping it in a KMS will be a secure option if it's possible. And the SWIT is nothing but a X509 certificate. We can extend it and see what it looks like. The important part that I want to highlight is this yellow text. As we see, the SPIFFE ID is inside the URI portion of the X509 version 3 subject alternative name stanza of this certificate. And it's really helpful, like I said, because I can now say that this application has this UUID that has been assigned to it by O-RAN, and claim that it is this application that it claims to be to anything, anywhere, essentially, transparently, irregardless of what I am talking to. And since the application have SWITs, we can establish a secure communication of the application to near real-time RIG platform with the SPIFFE minted SWITs. And in addition, since the xApp ID is already part of the SWIT, like we mentioned, the management service within RIG can extract the ID and deliver it to the app as part of the registration payload of the response, which we'll kind of observe in the next slide as well. So let's consider how these principles of SPIFFE can be extended and applied to a more broadly region to enhance the security of not only the xApp, but the entire SMO and RIGs essentially. So imagine a scenario where not just one individual xApp gets an identity, but like you get an identity, you get an identity, everybody gets an SWIT. So in this case, the SMO can have its own SWIT, or one termination, management services, and even the security function can have its own SPIFFE minted SWIT. And this way, we automatically have MTLS across the entire RIG as a side benefit. And using MTLS facilitated by SPIFFE effectively shields the RIGs against a lot of threat vectors, ensuring that all communication is secure and trusted within RIG. And we can take this concept even further. We can extend the use of SPIFFE beyond just the RIGs to include the entire O-Cloud. And by adopting SPIFFE as the identity control plane for the O-Cloud, we can ensure that every piece of software, every service, every system within the O-RAN ecosystem can authenticate and communicate securely. And by centralizing the identity management with SPIFFE, we reduce the complexity and increase the effectiveness of our security measures, ensuring that the O-RAN ecosystem remains resilient and trustworthy as always. So we have reached a fascinating part of our session, the fireside chat. It's my pleasure to welcome Daniel Feldman, a distinguished expert in SPIFFE and SPIRE, and also a well-recognized figure in the Zero Trust security community. Hi, Dan. Thank you for joining us today. We are all looking forward to gaining insights from your extensive experience and discussing the principles that we have covered here so far. Welcome.